Section P3 talks about functions and their graphs. So some things we'll look at today is using function notation to represent and evaluate functions, finding domains and ranges, sketching graphs, identifying different types of transformations, and classifying and recognizing combinations of functions. So just a few reminders about function and function notation. So if x and y are sets of real numbers, a real valued function of a real variable x from x and y is a correspondence that assigns each number x in your first set to exactly one number y in your second set. So your domain is the set of all of your x coordinates, and the number y is your range, or all the numbers in your y are your range. I'll keep writing on this line. So if we have the original equation, x squared plus 2y equals 1, it implicitly, so here's some vocabulary for you, it implicitly defines y as a function of x because your x and your y are still on the same side. So it's just the idea that you're saying y is a function of x, but we haven't come right out and said that. Now, if you were to solve the equation for y, so if we were to say that, if we were to solve it for y, so we have 2y equals 1 minus x squared, or we were to say that y equals 1 minus x squared over 2. So writing it in the y equals form, we're writing the equation in explicit form. So it's kind of like we're for sure saying that y is a function of x. So function notation, remember, is when we replace that y with the f of x. And so then what we're really doing is at the same time that we're telling you it's a function, we're telling you that x is the independent variable, and we're actually naming the function. We're calling it f. So that f of x, remember, is that f of x. If they were to say, f of 2, that would mean what is your y value when you substitute 2 in for your x values. So your function notation allows you to be a little bit less wordy. Instead of saying what's the value of y that corresponds to x equals 3, you can just say what is f of 3, and it means the same thing. So it's kind of that shortcut notation. So just a few reminders of how we evaluate function notation. And you're probably used to most of the time just substituting in numbers for x. If we had f of 2, we would say that we would then substitute a 2. So we would have 2 squared plus 7, and so we would say that f of 2 is 11. But in this example, we're going to practice substituting something that's more than just a number. So in A, when it says what's f of 3a, that means anywhere we have an x, we're going to substitute a 3a and then apply whatever is being applied to the x. So f of 3a would be 3a squared. So 3 and a are both squared plus 7. So we would say that that's 9a squared plus 7. For part B, f of b minus 1, we would substitute in a b minus 1. So we would say b minus 1 squared plus 7. When we FOIL that out, we get b squared minus 2b plus 1 plus 7. So we would get b squared minus 2b plus 8. And then part C, it gets even more complicated. So we have a couple things happening. We have the function where we're substituting x plus delta x. So if we have that, f of x plus delta x is going to be x plus delta x squared plus 7. So that's this first part. We just substituted that x plus delta x in there. And then it says we're going to subtract just our regular function, f of x, which is x squared plus 7. And then we need to divide it by delta x. This is getting us into a difference quotient, which we'll use in the next chapter. So there is a reason that we're doing all of this. So if you were to expand that x plus delta x squared, you would get x squared plus 2x delta x plus delta x squared plus 7. Remember to distribute your negative, minus x squared minus 7 all over delta x. Now go through and start simplifying. If you notice the x squared minus the x squared, the 7 and the minus 7. And so all you have left are terms that have delta x in them. So you have 2x delta x plus delta x squared over delta x. And since they all have a delta x, you can simplify that delta x. And so you're left with 2x plus delta x would be what that original function would equal when you make those substitutions. So domain and the range of a function can be described explicitly, or it can be described implicitly by an equation used to define the function. So the implied domain is a set of all real numbers for which the equation is defined, whereas an explicitly defined domain is one that's given along with the function. So here's a couple examples. So for the first example, if we had f of x equals 1 over x squared minus 4, and it told you that your domain is only the real numbers from 4 to 5, that would be explicitly defined. It's almost like they take the whole domain and they only give you a small set of values that you're actually going to use. So they make it smaller than what the actual whole domain is. Where the implied domain would just be that if we have the x squared minus 4 in the denominator, we know that x can't be 2 or negative 2, right? So the implied domain is kind of what's the most general domain. An explicitly defined domain would be if they really become specific about just part of that whole domain that you're able to use. So in example 2, we're finding the domain and the range of the function. So if we start with a, we know that underneath the square root, you have to have a number that's greater than or equal to 0. So we know that x minus 1 has to be greater than or equal to 0. And if we were to solve that equation, x would have to be greater than or equal to 1. So if we were listing the domain in interval notation, let's practice our interval notation, we know that 1 is the minimum. It can include 1, and it could go up to infinity, and we don't include infinity in our interval notation. So then your range, if you were to start looking at this, if you were to plug a 1 in for x, you would get 0, and you know that your y values all have to be greater than or equal to 0. So our range would be from 0 to infinity. All right, part B is your tangent. Now, without your calculator, I need you to think about tangent, and remember that tangent is the sine of x over the cosine of x. So when we're talking domain, we know that in this case that the cosine of x cannot equal 0. And remember with your unit circle, if you were to think about your unit circle, the cosine is your x values. So your x values would be 0 up at the top and the bottom, which is your pi over 2. So your domain would be real numbers not equal to pi over 2, and it would be every half of a rotation, which would be plus pi n. Your range for your tangent, remember that your tangent function looks like this, right? We have a bunch of asymptotes in there. So your range is all real numbers, which you could also write negative infinity to infinity. And then part C, we have a piecewise function. So here we have to look at the two different parts of the function. 1 minus x when x is less than 1. So this domain right here, for this one, would be if x is less than 1. So the minimum value for x would be, the maximum value for x would be 1, but we couldn't include it. And we would go negative infinity to 1. And then the range would be values the other domain would come from here, where we know that x has to be greater than or equal to 1, including 1, and we could go up to infinity. So if we were to put those two domains together, your domain here is still all real numbers, but it's your range that could be tricky. So if we had numbers that we were plugging into this top part that were less than 1, so if we plugged in a 1, we'd get 0. If we plugged in a 0, we would get 1. A negative 1, we would get 2, and so on. So this range would go from 0 to infinity. And with the square root, we know that that range goes from 0 to infinity. So if we were to combine those two and make it work for both, then our range would just be 0 to infinity. We would actually include 0, because even though this first one doesn't include 0, the second one does include the 0. All right, so now looking at graphs of functions, this isn't a bad little slide for everybody. This just gives you the graphs of what a lot of the parent functions are, kind of those 8 main parent functions. So just taking a look at those to have just that general reminder of what those parent functions are, because we're moving into the transformations in the next slide. So with transformations of functions, remember that if you're applying the transformation to the vertical graph, that won't be connected with the x. So if you're shifting up 2, that plus 2 is separate from the x squared. If you're reflecting it, that negative is not being squared. Where if you're applying it to the horizontal axis, it's going to be included with whatever is being applied to the x. So if you're shifting it left 2, we're going to say x plus 2, and that whole quantity will be squared. And then if we have everything here, if we were to look at this graph, we would see that x plus 3, so it's shifted to the left 3. This negative is a vertical reflection, so it's reflected over the x-axis, and then it would be shifted up 1. So here are your rules for your transformations if you need just kind of that quick little reminder of what's happening. Remember that your x's lie, right? So whatever it says the x is doing, it's actually doing the opposite. So for here, if it says x minus c, you would think it's moving to the left, but it's really moving to the right. And your y's tell the truth. So what's actually being applied is not to the vertical values, is what's actually happening. Something else is your combination of functions. So just remembering how to put functions together in that function notation. That can be kind of confusing. If it says f plus g of x, that means the same thing as f of x plus g of x. So you would add those two functions together. Same thing, f minus g of x would mean f of x minus g of x. F times g of x, f divided by g of x, you just take each individual function and apply that rule to it. And then another way that we can combine functions is the composite function. So when you see this notation f of g of x, it means that you're taking the entire g of x function and plugging it into the x values of the f of x function. So if we're going to practice finding composite functions, this first one, f of g, means that we're doing f of g of x. So we're taking the g of x and substituting it into the x values. So we would have 2 times the cosine of x minus 3. And then for part B, if we had g of f, that would be the same thing as saying g of f of x. So in this case, we're taking the 2x minus 3 and substituting it into the x. So we would have the cosine of 2x minus 3. And then the classification of functions. This comes back into your symmetry test that we did in the last section. So if you have symmetry where the f of negative x is the same as f of x, this just means you have reflections over the y-axis. So if you have reflection symmetry over the y-axis, it's an even function. And if you have symmetry about the origin, then you have an odd function. If you have symmetry across the x-axis, you don't have a function because your graph wouldn't pass the vertical line test. So if we need to determine whether the function is even, odd, or neither, and then find the zeros. So first starting with A. So if you remember from that last section, when all of our exponents are odd, then we know that we're going to have odd symmetry. But in order to determine that or show that, remember we have to do that test where if we have our x and our y points, that would say that when we substitute in a negative x and a negative y, we would get the same function. So if we said we have y equals x cubed minus x, that would give us the same thing as negative y equals negative x cubed minus a negative x. Or negative y equals negative x cubed plus x, which would give us y equals x cubed minus x, right? So we have, in that case, we have an odd function. Because remember, your odd functions have that symmetry about the origin. And your even functions have the symmetry across your y-axis. So the second part of this says find the zeros. So if we need to find the zeros of x cubed minus x, we would plug a 0 in for y. And here we're going to factor into x squared minus 1. So this would factor into x times x plus 1, x minus 1. So our zeros would be at 0, negative 1, and 1 for our x values. I guess I don't need that last little parenthesis. So when we look at our next graph, we know it's not odd because it has those even, but maybe it's even because we have those even exponents and constants. So remember when we think it might be even, that everything that was an x and y means that our x's are reflected. So if we plugged in a negative x, we would still get that same thing. So again, if our function started as y equals x squared minus 4 over x squared plus 3, that would mean that we could say y equals negative x squared minus 4 over negative x squared plus 3, right? And when we square everything, we do end up with that x squared minus 4 over x squared plus 3. So to find the zeros, we're going to plug a 0 in for y. So 0 equals x squared minus 4 over x squared plus 3. And remember, to find the zeros, we're really looking for when this function would equal 0. So this will equal 0 when your numerator equals 0. So we are really just having to solve for when does x squared minus 4 equal 0. So when does x squared equal 4? And when you take the square root of both sides, you get plus or minus 2 for the zeros. The only thing you need to check is go back and check that in your denominator that doesn't also give you zeros in your denominator, which would then give you a hole in your graph at that point.